Okay, so we undo squaring, so we're going to take the square root of both sides. So I get an x over here. What do I put on this side? Very good. Plus or minus radical 2. Because when we take the square root, we have to account for the fact that the number you plug in gets squared. So it doesn't matter whether it starts as positive or negative. Both of those would turn out positive in the end. Okay, Christopher, how do you do this one? Cube root? Cube. So we're going to cube both sides. These undo each other, so we get an x on this one. And then we get 125. Okay, he's smiling. He must like these starter questions. Okay, and then this one right here? X to the sixth. Okay, how does that differ from this one right here? It'd be x to the fifth. Okay, so if we're really? This is a plus? Do we get x to the fifth? You can't combine them, right? Because they're not like terms. Okay? If it were multiplication, then we'd get x to the fifth, right? Okay, so you got to keep straight. Like terms, what happens when we multiply them, what happens when we have a power to a power and stuff like that. Okay, so we want to make sure we don't lose track of those details. Okay, well, now that we're familiar with exponential functions and logarithmic functions, we can solve equations that involve those. So we're going to be solving exponential and logarithmic equations. The cool part about this is we're going to use the same tools that you use for the equations that you've been solving for years. So when I solve this one right here, there are a couple different ways that I can do this. Okay? So on something like this, the easiest way to solve an equation here, well, this is, let's see, what function is involved here? Is this an exponential or a logarithmic equation? It's an exponential equation because that's got exponential base 2 in it, right? So the easiest way to solve an exponential equation is if you can write both sides using the same base. So if I can do 2 to the, let's see, 2 to the 3x. Over here, can I write 8 with a base of 2? I can. I can write that as 2 to the third. Now, if the two sides are equal and the bases are equal, what's the only way the two sides could be equal? Yeah, is if this exponent equals that exponent, or in other words, if x is equal to 1. Now, they're not all that easy. I mean, everybody knows 8 would be 2 to the third. Okay, so they get a little bit more difficult. So let's take a look at this one right here. Again, the idea is to write both sides using the same base. Well, here, this was already a base of 2. I can write 8 with a base of 2. Can I write 8 with a base of 4? No, 4 to some power equals 8? Well, I could, but it would be an ugly number that I'd have to figure out. So it would be a lot better if I did this. Let's write this as 2 squared raised to the 3x. And let's write this as 2 to the third. If I have a power raised to a power like we reminded ourselves of up above, this is going to be 2 to the 6x, because I multiply them when I've got a power raised to a power, equals 2 to the third. And again, if the two sides are equal and the bases are equal, then the only way they could possibly be equal is if the exponents are equal. So that would be 6x equals 3. That means x equals 1/2. And again, you'd always want to keep in mind, this is the answer to an equation, so it would have to work when you plug it back in. So if I plugged it back in, I'd have 4 to the 3 times 1/2. So that'd be 4 to the 3/2. Square root of 4 raised to the third. That is 8. Okay, so it does work. Okay. When I have a problem like this, again, a little bit larger number, but hopefully we've seen this enough that we recognize it. Can I write both sides using the same base? Yeah, this is going to be 3 to the 2x minus 1. This is going to be 3 to the fourth. Again, you ought to recognize some of those perfect cubes, perfect fourth powers, and so forth. So this would be 2x minus 1 equals 4. Add 1 to both sides, so that's going to be 2x equals 5. So the answer on this one is 5/2. Okay, are there any questions? You can. We're going to do it another way. Okay? So that's solving, writing both sides using the same base. Okay. But that only works if it's a pretty easy problem, if they're easily recognizable numbers. Okay, if we can't solve something in exponential form, and that's what this is, we could write it in logarithmic form. So here's what we're going to do on this problem right here. There are a couple different ways that we can do this, so please watch and pay attention. So it says, write your answer in exact form and as an approximation correct to 3 decimal places. So can you write 5 and 8 using the same base? You can't. Okay? So what I'm going to do is I'm going to write this in logarithmic form. So this is going to be log base what? Log base 5 of 8 equals 3x. Now you'll notice that this is just a number, and I've got 3 times x. So if I had 14 equals 3x, how would I solve that? Divide by 3. So let's do the same thing here. We're going to divide this side by 3 and this side by 3. So I get x equals log base 5 of 8 equal or over 3. Okay, so this right here would be the answer. Now, that's the exact answer, right? That's the exact answer. We want to be able to come up with a decimal approximation. So decimal approximation for this. Do you have, let's see, do you have a log base 5 on your calculator? Nope. Okay. So we went over the change of base formula last time. Here's what we can do. I like ln, so I'm going to do the ln of 8 over the ln of 5, and then I'm going to divide that by 3. Or if you wanted to think of it as 1/3 times the ln of 8 over the ln of 5. So let's grab a calculator. Let's type this in correctly. So this is going to be ln 8, close the parentheses, divide by ln 5, close the parentheses, and then we're going to divide that answer by 3. And our decimal approximation is, and then we said 3 decimal places, right? So that'd be 431, 0.431. So here is our approximation, and here is our exact answer. And you're going to need to be able to do this on the test. Okay, now, how can you check and see if this is right? Let's take the calculator and let's plug it in here. Let's do 5 raised to the, that would be 3 times that last answer right there. I'm going to put in 0.431. Now, if I did this right, I should get 8, correct? Close. A little more or a little less than 8? It's going to be a little more because I rounded this number up, and there it is right there. Now, if I plugged in that number exactly, so if I did 5 raised to the 3 times that last answer, it's exactly 8. So did we get it right? Okay. All right, so let's take a look at this next one. Again, you're not going to be able to write 4 and 20 using the same base. So we're going to put it in logarithmic form. So this is going to be log base 4 of 20 equals x plus 1. So the only thing we need to do to solve this is move that over to the other side. So this is going to be log base 4 of 20 minus 1 equals x. And I would do this just to make sure we're clear. I would put that in parentheses. If we were going to get a decimal approximation, again, I'm partial to ln, so we're going to do ln 20 over ln 4 minus 1, and that's going to give us our decimal approximation. So let's see what we get there. ln 20 divided by ln 4, subtract 1. 1.161. And again, you could check to see that that's right by plugging it in to that exponential there. Okay, are there any questions? Okay, some people get a little scared of something like this. I mean, it looks like it has 2 variables, but it's e a variable. It's not. It's the natural number e, 2.7181, blah, blah, blah. Okay? So, how can I undo this exponential? Yeah, I can write it in logarithmic form. So I can take, this would be log base e of 20 equals t. Or I could do this. Everybody watching? What if I took the ln of this side and ln of that side? What does ln do to exponential base e? It undoes it, so it makes it a t. And on this side, it would be the ln of 20. So isn't that what this represents? Log base e of 20. Okay, would be the ln of 20. There's the exact answer. Let's get our decimal approximation. Just grab the calculator, type in ln 20, 2.996. And again, you could plug that in into this right here. You could do e to the 2.996, and it should be about 20. Okay, are there any questions?
Quick question.
Yeah.
So how would we be able to do the log base e of 20 on the calculator if we didn't do the natural log?
Now say that again.
So if we were just going to plug in the log base e of 20 equals t, how would we do like the reverse thing? So like log over 20, like log base 20, like log 20 over log b.
So this is, well, you could just, so do you want to use natural log or common log? Log base e or log base 10? If do log over log e and do ln 20 over, whoops.
Oh yeah. Right.
Do ln 20 over ln e. The ln of e would be 1. Okay? So the denominator would work out. And then you just have an ln of 20. Is that all right? Okay. Christopher, you were going to say, can't we do this a different way? What would you do? Oh, these right here? You were asking if we could do these a different way. No? Okay. We're good? Okay. All right, let's take a look at this next one right here. This is problem number 24. It's either on your assignment or one very much like one on your assignment. How would we do this? Move 65 to the other side, so we're going to add 65. So that's going to be 7.2 to the x equals 65. And if I can't solve it in this form, I change it to logarithmic form. So this is going to be log base 7.2 of 65 equals x. And again, there's the exact answer. You could type it into your calculator as ln 65 over ln 7.2, or you could do log 65 over log, make that look better, log 7.2. We talked about last time, could you mix it? Could you do a log on top and a natural log on the bottom? No, got to be the same base on the top and bottom. What did you come up with? What decimal? 2.115? Okay. Is that rounded correctly? Okay. Stop and think for just a second. Should this number be an answer around 2? And shouldn't it be a little bigger than 2? So shouldn't we know before we even type this into our calculator, we're expecting an answer that's a little bit bigger than 2. Amelia, can you tell us why it should be a little bit bigger than 2? Okay, so if you square 7, you get 49. Okay, we want something a little bigger than 49. Our base is a little bigger than 7. Another way to think of it would be if we made this about 8 and we squared 8, that would give us 64. Okay, so it's got to be somewhere around 2, and definitely bigger than 2, but for the same reason there, that if we just squared 7, we'd only get 49. Any questions? Okay. All right, so let's take a look at this problem right here, some that we did earlier, by using inverse operations. Now, you can't do this on every single type of problem, okay? But on this one right here, if I took the log base 3 of this side and the log base 3 of this side, okay, it's kind of like taking the square root of both sides or cubing both sides like we did in the starter question. What does log base 3 do to exponential base 3? Yeah, okay, they undo each other would be the best way to describe it. They undo each other. So we end up with a 2x minus 1 equals, and what is log base 3 of 81? Log base 3 of 81 is 4. Then I can move that over. So I'd add 1. So I get 2x equals 5. So I get x equals 5 halves. Again, you don't have to do it that way, but you should at least be aware that you can do these using inverse operations. So this is exponential base e, right? What's the inverse of exponential base e? Like we were talking about up above. Take the ln of both sides. What do these do to each other? They undo each other. So I get a t on this side and an ln of 20 on that one. If I solved number 24 again, I'd have 7.2 to the x equals 65. What is the inverse of this function? Log base 7.2. So if I do log base 7.2 of this side and log base 7.2 of this side, this function undoes that function right there, and I get x equals log base 7.5, or sorry, 7.2. Sorry about that. 7.2 of 65. Now, do you need to do every single type of problem both ways? Absolutely not. Okay, the easiest way to solve this one is to write both sides using the same base. But if you get used to being able to undo a function, whatever it is, using its inverse, in this case we're becoming more familiar with logs and exponentials, you're going to be much better off when you take 1050, because in 1050 you're going to encounter problems that's the way you're going to undo them, is you're going to do a logarithm or you're going to do an exponential. So let's take a look at this next side. And again, sticking with the idea that there's more than one way to do each one of these problems. On this one, we're not going to go from logarithmic form to exponential form. What we're going to do is we're going to think about this in terms of inverse functions. So this function right here is log base 2. What undoes log base 2? Say it the right way. What's the inverse of log base 2? Exponential base 2. So what we do on these problems, you may not have learned this word before, but this is called exponentiating. We're going to take both sides and we're going to put it in the exponent. That's why it's called exponentiating. We're going to exponentiate both sides. So if I do 2 to this side and 2 to this side, just like we saw on these problems right here, what does exponential base 2 do to log base 2? Okay, what's the best way to describe it? They undo each other. So I get an x plus 1, and on this side, I have 2 to the 5th. Now, 2 to the 5th is a pretty easy number to figure out. What is it? 32. So this is x plus 1 equals 32. And if I move that to the other side, I get x equals 31. Now, with a logarithmic equation, you need to check and make sure that your answer actually works. Because when I plug it in, maybe I'm taking the log of 0, maybe I'm taking the log of a negative. Now on this particular one, if I plug it in, I get log base 2 of, what's 31 plus 1? 32. And 2 to what power equals 32? 5. So you see how that works? It does in fact work. Let's take a look at the next one. What's this function called? Or log base e. How do you undo log base e? Exponential base e. So you're going to exponentiate both sides with a base of e. These two undo each other, so we get x equals e to the negative 2.1. And the cool thing about this is, that's it. That's the answer. There's no moving around. That is the exact answer. You could type it into your calculator and get a decimal approximation, but that's the exact answer. Yeah.
Wouldn't you want to do the reciprocal since it's a negative exponent?
You mean write it like this? 1 over e to the 2.1? You could, but which is easier to plug into your calculator? Okay, take a look at part C here. You'll remember that when we've solved equations, typically we've isolated the variable part of the equation. When we solved radicals, we isolated the radical in the equation. When we solve a problem like this, we're going to isolate the logarithm. So the first thing I'm going to do is I'm going to divide both sides by 5. So this is what I get. I get log base 6 of x plus 1 equals 2. I take note of what function is in here. I'm taking the log base 6 of x plus 1. I'd really like the x plus 1 all by itself. What is the inverse of log base 6? Exponential base 6. So we'll exponentiate both sides. This function undoes that function. I get an x plus 1. And over here I get, let's just 6 squared. That's 36. So the answer is 35. Now, again, with a logarithm, you want to make sure that it actually works when we plug it back in. Make sure when you plug it in, we're not taking the log of a negative or 0. Does that happen in this problem? No, so it's going to work just fine. Okay, are there any questions? Okay, again, really quickly, this is the idea that these are inverse operations. But again, like I mentioned before, if you can't figure something out in logarithmic form, write it in exponential form. What's the base? 2. What's the exponent? 5. And what should it equal? X plus 1. So 2 to the 5th should equal x plus 1. Do I get the same thing I had above? Yes, I do. On this problem right here, what's the base? E. What's the exponent? It's the answer to the logarithm, negative 2.1. And what should it equal? Should equal x. So I get exactly the same thing by converting from logarithmic form to exponential form and vice versa. I also should be able to think about it in terms of inverse functions, inverse operations. But again, on this one, you're still stuck. You do have to divide both sides by 5. So I have log base 6 of x plus 1 equals 2. Again, the base is 6. The answer to the logarithm is the exponent, and it should equal x plus 1. You'll notice that I'm getting exactly the same thing that I had up above. It's just in the opposite order because we typically write the exponential first and then what it equals. Okay? Are there any questions? Sure? Is this pretty easy? Okay, I'm hoping it's pretty easy. I do want you to think about it in terms of doing these both ways. So think about it in terms of converting from exponential to logarithmic or logarithmic to exponential, but also in terms of using those inverse operations. That is a very important idea. It's a good skill to have. And this is it, right? Yeah.
So on the test, are you going to say solve this by doing the inverse operation?
If I give you instructions to solve it a certain way, follow the instructions. But if it just says solve it, as long as you're showing your work and I can follow it, either method would be fine. Good question. Anything else? Okay, let's take a look at the last couple. It says we need to know how to solve exponential and logarithmic equations, and we got to remember some algebra. So what's the easiest way to solve an exponential equation? Should we take the log base 2 of both sides? Or if it's like this, can I write both sides easily using the same base? Yeah, on this particular one, that's probably the easiest way to go. So this is x squared plus 3x. And on this side, this is 2 to the second. Again, the only way the two of these can be equal is if x squared plus 3x is equal to 2. Is if that exponent is equal to that exponent. Well, at least I've got the exponentials out of the way, but now what's my problem? I've got to solve this. And this is a quadratic. It's got an x squared term and it's got an x. So what do we do with this? We could complete the square if we wanted to. We could set it equal to 0. We could use the quadratic formula. We could factor it. Any one of those techniques would work. Let's take a look at this. We definitely want to set it equal to 0, I think. Completing the square would be a pain in the butt. You'd end up with 3/2, and you have to square that and add it to both sides. You could plug this into the quadratic equation right away, or let's at least take 2 seconds and think for a minute. Could we make this easy on ourselves? Are there numbers that multiply to be -2 that combine to be +3? Nope. Multiply to be -2, combine to be +3. You'd have to have a +2 and a -1 or vice versa. Okay, you're not going to make a 3 out of those. So we're stuck using the quadratic. So if we use the quadratic, this is going to be, let's see, Elaine, you want to sing the song for us?
No.
Okay, Elaine's not going to sing the song, so it's going to be the opposite of b, so that's going to be -3. B squared, that's going to be 9 minus 4ac, and I said don't skip this work right here. So that's going to be a 1 and a -2 all over 2a, so that's going to be a 2. And then I said write this work up here, write down 9, and figure out, are we adding or subtracting? We're going to be adding 8. So here's what we get. We get -3 plus or minus radical 17 all over 2. And this is why it's helpful to be able to write this as 2 separate pieces. One of them is -3 plus radical 17 over 2, and the other one is -3 plus, or excuse me, minus radical 17 over 2. Now, let's throw those in the calculator and get a decimal approximation for each one of those. Go ahead and type it in. Compare it with your neighbor. What mistake do people typically make with this? Anybody know? Parentheses. Okay, the entire top has 2 terms in it. You better put it in parentheses so it does the whole top divided by that 2. So I'm going to start with a set of parentheses. -3 plus square root of 17. Got to close the parentheses twice, divide that by 2. There's an answer. And if I just recall that, all I have to do is just change this to a minus, and that gives me the other answer. Now, my question for you is, do they both work? Do you have to be careful with exponentials? Not exponentials. You can plug in anything you want. So my bet is both of these work, but let's check. Okay, everybody watching? Okay, here's what I would do. If you've got a calculator like this, if not, you can use the answer button on yours. So I'm going to take that last answer and I'm going to do 2 raised parentheses. I'm going to take that answer and I'm going to square it, and then I'm going to take plus 3 times that answer. Now, what I've typed in right here is this side of the equation. I didn't even round. I used that last answer there. So if I did this correctly, if that truly does work, what should this equal? Should equal 4. Ooh, nervous there for a second. It does equal 4. It works just fine. I'm going to recall that last one. Okay. Now, on your TI, whatever, you can do the same thing. You can recall commands by just hitting the up arrow. So I'm going to have it recompute. Whoops, not that one. Oh, what happened there? Whoops. Must have turned that off. So it doesn't have that on there anymore. So whoops. Parentheses -3 plus square root 17. Tell me if I do something wrong. There's that one answer. And then it was 2. And then the answer squared plus 3 times the answer, right? They both work. Okay? And again, what I was going to do is, whoops. If I go back and I change this, and then I just recall that, it's going to take the most recent answer and plug that in there. They both equal 4. Okay? So you can save yourself some typing if you use the up arrow on yours or you use the second enter to recall things on this. Any questions there? Okay, all right, let's take a look at this last problem. This one says log base 2 of x squared plus 1 equals log base 2 of 10. Okay, well, just like here, we got the bases to be the same, and then the only way that they could be equal is if the exponents were equal, or, everybody watching? You don't have to write this down. If I took the log base 2 of both sides, wouldn't they undo each other, and you'd get an x squared plus 3x on this side, and you'd get a 2 over there? Okay, well, look what I've got here. I've got a log base 2 of this stuff equals log base 2 of 10. So what does that mean? That means that stuff, x plus 1, has to equal 10. Subtract 1. Or you can put it on the same side, factor it using a difference of squares. You could write this. X minus 3, x plus 3. What's the answer whether you take the square root using the square root property or you factor it? Plus or minus 3. Do they both work? Can I take an answer of 3 and an answer of negative 3 and plug those back in and make that equation true? You can. Okay, now listen very carefully. Remember, I've been making a big deal about the domain issues that a logarithm has. You can't plug in a negative or 0. But if you listen carefully, what I said was you can't take the log of a negative or 0. When I take the negative 3, what happens to it first? Square it. What do you get? Positive 9. Add 1, 10. Log base 2 of 10 does equal log base 2 of 10. So I get to keep both of those answers. That doesn't always happen. It happens on this particular case. Okay, are there any questions? Okay, so please be familiar with both of those ideas. The fact that you can solve a logarithmic equation by exponentiating or by writing it in exponential form, and you can solve an exponential equation by taking the log of both sides, okay, or by writing it in exponential form. Both of those techniques are important. They're both very useful. I'd be aware of both of them. We have one more section to cover, and then we're done with Math 1010. Of course, you got to take a test. You got to review for the final. You got a couple packets to do, and then the test is, what day is it? Thursday of finals week, a week from Thursday. Okay?
We have a test this Thursday.
Okay. All right. Have a great day. Thank you.